my presentation is about how we use math and physics, nonlinear mathematics, and statistical physics to develop treatments, to develop invasive and non-invasive stimulation technologies that enable to change network topology for therapeutic purposes. And it's specifically about a new treatment for Parkinson's, non-invasive, quite promising according to clinical results. Let's start with Parkinson's. Although this approach is by no means restricted to Parkinson's, I focus on Parkinson's in this talk. Parkinson's disease is characterized by abnormal neuronal synchrony. Synchrony appears to be nice, aesthetic, harmony, representing harmony, whatever. Too much of synchrony means that neurons are not free to do their information processing separately, and hence it's typically an abnormal feature. Abnormal synaptic connectivity is also a hallmark of Parkinson's disease, and it's basically a reaction to the lack of dopamine. Let's start with deep brain stimulation. Deep brain stimulation is, to a large extent, empirically developed treatment that is still not really fully understood. What you see here is a right-handed Parkinson's patient who had to retire because of the strong tremor as a right-handed person. And he got an VIM, ventricular intermediate nucleus thalamic electrode implanted in the VIM of the thalamus. And the important message comes now. He's one of the patients who responds really, not all patients respond that well. But the important point is the effects of standard high-frequency stimulation do not persist. They vanish when turning off stimulation within seconds to minutes with respect to tremor. And in this specific target area, one typically observes a so-called rebound phenomenon, or minutes up to half an hour with respect to the other symptoms like bradykinesia, rigidity, and so on. High-frequency deep brain stimulation was certainly a game changer, but has relevant limitations. It doesn't have long-lasting therapeutic effects, meaning it requires quite some stimulation, substantial amount of stimulation. The more you stimulate, the more you inevitably stimulate structures you'd not like to stimulate, since this causes side effects. And in the meantime, there's really a term for this. It's called DBS, deep brain stimulation induced movement disorders. And the other thing is, it is in the same way as pharmaceutical approaches, DBS does not really help with so-called axial symptoms. Axial symptoms are balance issues, gait issues, and also speech deterioration. Typically, when there's a speech impairment, is often part of a symptom of Parkinson's disease. It gets worse under DBS. A while ago, I started a different approach, modeling approach. The very goal was to counteract abnormal neuronal synchrony specifically by desynchronization. And the important point is, if you take into account, just from a model, as from mathematical standpoint, computational standpoint, if you take into account plasticity, for example, spike timing dependent plasticity, even simple neural networks are multi-stable. And this led to the concept of desynchronization-induced changes of topology, basically of inducing long-lasting desynchronization. So you have, for example, just schematically a network, strongly connected with strong synaptic connections. You have these strong synchronous firing. This is a raster plot. This is the time axis. That's neuron index. You desynchronize the neurons adequately with appropriate stimulation parameters, and typically can do that in certain parameter ranges. And then the synaptic connectivity decreases and the neurons firing in desynchronized way. So it's basically, just for the sake of illustration, like in a potential landscape, although the attractors are certainly more complicated or complex. One of the techniques that turned out to be very, very robust for clinical use is coordinated reset stimulation. Coordinated reset means the following: we have a neural population, a bunch of balls here representing a neural population. Each gray ball represents a neuron. We do not, but what one does for standard high frequency deep brain stimulation, you have an electrode implanted in such a neural population, you have an electrode implanted, and you look which contact is most optimal, or sometimes one takes combinations, 1 or 2 contacts combinations, and then you increase the amplitude as high as possible in order to, as close as possible to the sensory threshold of side effects. If you were to go even higher, you'd reach motor side effects. So it's really a strong type of intervention. And it's the thinking behind it in some sense, although that's not really proven, the thinking from a clinical perspective is that the more current you inject, the more you might replace the dopamine medication. And so what we do is coordinated reset is the following: we do not stimulate, we do not try to sort of block or inhibit or whatever deep brain stimulation does with as many neurons as possible through 1 or at most 2 typically stimulation contacts. We want to stimulate in a way less invasive manner, in the sense that we stimulate different subpopulations at different times. And the stimulation is weak in the sense that it does not block or inhibit neurons. It just causes a phase reset. So if we do this, and to this end, we stimulate different times, at different times, different sites, different subpopulations at different times. This causes cluster states, and they typically are often run through transient desynchronized states. But the important point is what happens on a slower time scale. So if you take into account synaptic plasticity, the really interesting thing happens. It's not just an acute type of desynchronization that relates to a reduction of symptoms, but by means of delivering these coordinated reset stimuli, and these are just weak electrical bursts, and it's delivered with typically random sequences, but based on a periodic backbone. A cycle is in the range, but it doesn't need to be in the range of the abnormal pathological rhythm. We typically deliver a couple of on cycles with stimulation, followed by a few off cycles. And this is on the one hand to make use of the induced transitory desynchronization, but it's also in order to enable the neurons to process information in a physiological manner during the stimulation process. Now, the important point is what happens if these neurons are plastic, are adaptive. One important mechanism is already introduced to some extent by Hebb in the late 40s, is spike timing dependent plasticity. So let's assume, or let's consider a neuron A and a neuron B, and they fire at different times. They produce action potentials at different times, and the delta T is the spike timing difference. Now, here's what you see. It's a spike timing dependent plasticity curve that's fitted to experimental data. The x-axis is this delta T, the spike timing difference. The y-axis is the change of the synaptic weight occurring after such an event. And as you can see, if this comes first, if A fires first and shortly after B, we have a strengthening of the synapse, whereas if B fires first and A follows, we have a weakening of the synaptic weight. And strengthening and weakening anatomically means, strengthening means that the synapse gets stronger and stronger, larger, is more vesicles, whereas the weakening means it really shrinks like rays and gets smaller and smaller. In some sense, from a biological perspective, what it means is only those synapses should survive that actually do their job, in the sense that they should if A typically fires before B fires, then this synapse makes sense. Otherwise, it doesn't make sense and should just be pruned. Now, let's assume, for the sake of argument, we had a control technique that allows us to keep the delta T of these events within an interval of 2 epsilon. Now, and we assume that the spike times, the delta t's within this interval are uniformly distributed. Then it's an easy thing. We just have to integrate over the curve from within this interval given by the 2 epsilon width. And here you see what happens. So the x-axis is the epsilon. So small epsilon means coinciding neuronal pulses, action potentials, whereas larger values of epsilon means that they are uniformly desynchronized or uniformly distributed. And what we see is that for more or less coinciding synapse action potentials, the synapse gets stronger and stronger. That's the Voltairean principle. And for larger epsilon, so in other words, for desynchronized firing, the synapse gets weaker. And this led to this concept of desynchronization-induced reduction of synaptic weight. So what we want to do with desynchronization is not just acutely, meaning during stimulation, counteract the abnormal synchrony in order to cause a relief, in order to reduce symptoms, in order to reduce disease-related synchrony, but in order to induce a reduction of synaptic weights, in this way causing a long-lasting desynchronization. And this is illustrated here. What you see here is a phase oscillator, very simple model. Phase oscillators, at that time, very simple model. Phase oscillators, Kuromoto model with synaptic plasticity. The y-axis, the x-axis is time axis. P is the percentage of neuron firing per time unit, so 20, 40, 60%. And this is what's shown with high-frequency stimulation. High-frequency stimulation in this model simply causes a block high-frequency entrainment, hence block of the neurons. We immediately turn off the neural firing. As soon as we turn off stimulation, the synchronized activity comes back immediately. And this is CR stimulation, and on purpose, at a very specifically or on purpose, very, very weak amplitude. And as a consequence of the weak amplitude, what happens is shown here. So again, the x-axis, the time axis, y-axis is the amount of synchrony, 0 is min, 1 is max. And since the amplitude is so weak, we do not immediately induce a desynchronization during stimulation, but we induce sort of an intermediate or weak desynchronization. But this is enough in order to induce this process, this very process, and that's key. So again, the x-axis, time axis, the y-axis is the mean synaptic weight. And what you see here is that the mean synaptic weight continuously decreases over time. You turn off stimulation and the neural population remains in a stable, desynchronized state. And that's the very goal. And the question, of course, is how do we do this best? And the first few slides show you the initial studies on electrical stimulation, deep brain stimulation, and then I switched to vibrotactile stimulation. We did a study in monkeys, MPTP monkeys, Parkinsonian monkeys. Monkeys rendered Parkinsonian by means of MPTP, a neurotoxic substance. We used macaca mulata. Macaca mulata, when rendered Parkinsonian, do not have tremor, only akinesia and rigidity. And that's an advantage because then you can monitor treatment effect by monitoring movement production rate objectively. Apart from that, we also, of course, did video rating, blinded video rating. So these are the two stimulation patterns. So this is conventional high-frequency stimulation. Typical parameters is 130 hertz. And this is coordinated reset stimulation, where we have these weak, brief electrical bursts to desynchronize the abnormal synchrony. This is an example. This is a monkey. This is seconds, so 16-fold velocity. That's the measurement cage. So the monkeys were in that measurement cage with a light barrier system every day for 90 minutes. And what you see here is a little head that protects the electrode from being pulled out. So the monkeys were stimulated externally. Since the monkeys are some like 1.5 to 2 feet high, or 1.5 feet high, and small creatures. And the IPGs at that time, the implantable pulse generators, were simply too large. It was not possible to chronically implant them, therefore we stimulate them externally. Only 2 hours on 5 consecutive days. So in total, it was only 10 hours stimulation. And this model is very well understood. I did this together with Thomas Bourreau, Evan Bézard, Vasilis Meissner, one of the leading groups in MPTP at that time, MPTP monkeys, electrophysiology. And it's very well understood. So in these monkeys, due to the MPTP treatment, they only have between 5 and 10% of the dopamine producing cells that survive. So it corresponds, of course, to very late stage Parkinson's. Now, the same monkey, after the first 2 hours stimulation, so they were put into what's called a primate chair with their arms fixed. They tolerate being there. If you work on them, if you give them a banana or whatever, feed them for 2 hours. And in that primate chair, they were stimulated for 2 hours and brought back into the cage. And this is now the same monkey. And the important thing is the monkeys were completely off Parkinson's medication during the entire study. So this is the same monkey again. These are seconds, so it's 16-fold velocity to show you 10 minutes window. And you see the monkey behaves with respect to movement production like a normal monkey. There's no difference. Although there's a massive lack of dopamine. Only 5 to 10%, as I said, dopamine producing cells survive this treatment. Goes on like this. We did a crossover design and that's the important point. I mean, at that time, and we're still in that situation, of course, at that time and still now, we only use qualitative predictions. We had simple models, and the prediction was we can induce long-lasting effects. We don't know the time course or the time it takes to ramp to accumulate the necessary changes, and to know in order to observe long-lasting effects and how long the effects will last. But nonetheless, the study design is massively informed and relied on our computational work. So what we did, we had 5 days blocks where the monkeys were either not stimulated. This was the MPTP baseline. So the monkeys were stable, didn't change. The movement production didn't change or hardly change. And then we started with a 5 days block with a CR with DBS-like intensity, meaning the same amplitude of the pulses. And then we measured the potential after effects as soon as they turned back to baseline. We delivered the same. And then the next 5 days block, this was CR with low intensity, meaning a third of the amplitude of the single electrical pulse, which was predicted based on computational modeling, was predicted to be way more effective. And then finally, we did classical DBS stimulation. And of course, the parameters were calibrated as it is done in monkeys, very similar to humans. And just briefly, so this is what you see. This is the movement production rate, integral movement production rate during the 90 minutes. This is the mean of all monkeys and overall 5 days, the MPTP baseline. So just a very weak movement production rate. These are the 5 days. So the monkeys come after the 2 hours of stimulation, they come into the measurement cage for 90 minutes and are measured, and you see it's a non-significant increase, non-significant simply because it's 90 minutes and the effects of high frequency stimulation are gone after 30 minutes. And then these are the first 5 days post stimulation, and you see that the after effects are completely gone. And this is CR with the suboptimal based on computational modeling. Suboptimal, high intensity, we see some after effects at the first 5 days. And this is the important point. You see how low intensity, you have a huge amount of movement production rate during the days of stimulation, and they last for a month compared to statistical testing compared to baseline. And this was now independently confirmed by a number of studies, independent groups. We have a pilot study with unilateral, that's an important point, unilateral at that time. For technical reasons, we weren't able to stimulate bilaterally. So we studied patients, we simulated patients unilaterally, also in an externalized mode, meaning we didn't implant, we only implanted the electrode, but not the cable and the IPG, the implantable pulse generator. Patients were stimulated for 3 days, 2 times 2 hours a day, so in total 12 hours with an external stimulator. And this is a typical patient, 49 years old patient, right-sided patient. Patient also suffered from a dystonia. It's an additional complication in Parkinson's disease. Dystonia is difficult to treat. Also deep brain stimulation. So the patient was instructed to stretch her fingers, but she's not able simply because of the dystonia to do so. This is now directly before stimulation. See the patient. We record EEG, muscular activity, accelerometer, ECG, local field potentials, and this is now about 20 minutes after CR stimulation. And the symptoms are gone. And remarkably, also dystonia. Dystonia doesn't respond well to SDN stimulation. Typically takes some like 6 weeks or so to see some effect. And the important message is this. So this is 1 hour after turning off CR stimulation, and you see that the effects persist, symptoms do not come back. And this is very, from a clinical perspective, very different to what we observe with standard deep brain stimulation, where symptoms come back as soon as you turn off stimulation, as you've seen before. And also from an electrophysiological standpoint, it's also very different. So it's the same patient, and what we did was before and after, in the morning and in the afternoon, before and after the 2 times 2 hour stimulation, we recorded from the same from the depth electrode. And what you see here is the abnormal activity recorded from the depth, from those contexts that were also used for stimulation. So x-axis is frequency, y-axis is spectral power. This is before stimulation. You see the pronounced peak at around 5 hertz. And this peak at around 18 hertz, that's related to akinesia and rigidity, and this one's related to tremor. And this is the situation 1 hour after in total 4 hour stimulation. So the peaks are gone for at least, in this case, 1 hour. And this is very different compared to clinically effective high frequency stimulation, because this peak reverts within 12 seconds. And this one is basically reverts even more quickly. Comes back even more quickly. And just briefly, I don't want to go through this in great detail. And we've seen this also in a group analysis. Here you see the motor scores based. So this is the motor score, the relevant clinical exam of the motor activity from top to bottom, head to toe. And you see we have cumulative effects, nice, beautiful, significant overnight effects, and they correlate also with a significant decrease of the abnormal beta band. And these are concerning, of course. One has to be careful because we did not directly compare this to high frequency stimulation, but this is an effect size comparable to after what you achieve after six weeks of deep brain stimulation. Now, the goal is to provide patients a treatment that doesn't require implantation. In order to do the same thing non-invasively. Even there are many patients who do not want, who really massively object to any type of invasive treatment. So even if you show them these beautiful videos, they say never any drilling, any electrode into my brain. And it's understandable. I mean, the invasive treatments do have risks, come with risks, hemorrhage, infection, wound infection, different types of infections. And in a few percent, simply because of the invasive nature of this treatment, these side effects are inevitable. So based on computational modeling, again, there was the prediction we could do this. We should be able to do this non-invasively by means of sensory stimulation, simply because it's based on, these computational studies are based on experimental studies in the 1980s that have shown that you can easily reset a rhythmically active neuron with all sorts of stimuli, being synaptic, being axonal, being somatic, even different types, not only electrical stimuli. And the important point is now a group, Lenz's group, Weiss and co-workers have shown the following. If you vibrate, for example, the fingertip or someplace in the hand or in the face, if you perform a vibration and if you record in patients, and they've shown that in Parkinson patients, patients with other types of movement disorders, for example, patients with essential tremor, dystonia, patients with chronic stroke, if you then record from the part that is the primary sensory relay nucleus, human thalamic somatic sensory nucleus, what you see is a phase entrainment of the discharges of these neurons, thalamic neurons. So what you see here is the so-called cycle histograms. So the y-axis is the cycle. This covers one cycle. And this is just the histogram. So in case there were no relation between the peripheral vibration signal and this discharge, it would be just more or less a flat line. But what we see is that we induce beautiful phase entrainments, and that's the important point. We do not aim at suppressing neurons or inducing abnormal rhythms. We aim at controlling the neurons' discharge times, and therefore this phase entrainment is sufficient. And the question, of course, is which part of the body to start with. And I've chosen the fingertips simply because of the huge representation. So what you see here is the volume and the sensory map, cortical map. Same holds for the motor cortical map, and the corresponding body parts. That's the corresponding so-called nucleus. And you see that the hand and the fingers have a huge representation. Many neurons are coding, are responsible for processing information coming from the fingertips. That's very important because that means, although it's a small percentage of the skin that we are stimulating, nonetheless, the cortical volume we're actually reaching is huge. And we've developed a glove system where we stimulate with very robust vibrotactile stimulators, vibrators, where we stimulate the fingertips. And this is how the stimulation pattern looks like. So we basically we do the same thing as for deep brain stimulation. We basically replace an electrical burst delivered through depth electrodes by means of this vibratory burst. So it's 250 hertz vibratory burst, constant indentation. So the only thing is that we turn on and turn off stimulation, vibration. And in this way, we selectively stimulate one type of mechanoreceptors because we don't want to stimulate all sorts of mechanoreceptors, having different propagation delays so that the signals in the brain arrive at different times. But it's a selective type of stimulation of a specific mechanoreceptor, specifically and particularly sensitive to this 250 hertz vibration. The cycle length is 666 milliseconds, corresponding to 1.5 hertz stimulation. So it's typically perceived by patients and also healthy subjects as neutral or relaxing. The vibration amplitude is weak, perceptually weak, meaning you can do all sorts of things while you do this. You can be on the phone, you can read, you can do light workouts, or you can walk around or jog. Of course, watch TV and things like that. This is a 3-month pilot study first to show you the clinical data and some videos to illustrate that, and afterwards I round up with the role of maths and physics to further develop this treatment, to further improve this treatment. So what you see here, we at this time we wanted to do a study in 10 patients at least, aiming at 20, but then we were hit by COVID and had to stop after 6. That's the reason why it was only 6. All of the data I'm showing you in the next few slides are from medication off states, meaning patients went through a rigorous medication withdrawal. So depending on the half-life of the Parkinson's medication, their medication was withdrawn between 12 and 48 hours in order to get rid of any pharmaceutical interference. So that's the naked situation of the patient, so to speak. All of these data points are medication off data points, exams. So what you see here is the so-called acute effect. When the patient comes in at 8 o'clock in the morning, the clinical exam that covers head to toe, motor control from head to toe, and tremor and rigidity is done. And then the patient gets no meds, stays off medication, which is normally not trivial and really painful for patients. Parkinson's patients, all of these patients were advanced stage patients. You will see that in the videos. Several of them were deep brain stimulation candidates, came into our deep brain stimulation program and tested the glove. And then at 3:30, the final exam was done. And remarkably, patients, although they didn't get their medication and were off medication for a really substantial time, even improved significantly. And what you see here is the baseline visit and 3-month visit. So the patients went home, did 2 times 2 hour stimulation a day, 2 hours in the morning, 2 hours in the afternoon or evening, and came back after 3 months. And again, these exams off medication, after medication withdrawal, we see a significant decrease. Now, the important point is that's statistically significant. The question is, how do the single patients behave, and is there a clinically significant improvement? It's not just about statistics. And in order to ask this, there's a concept called minimally clinically identifiable difference, the MCID. And the MCID provides you with a threshold. If you exceed or fall below, in this case, in terms of a reduction, the threshold, your patients is known from large validation studies that patients perceive this as a really clinically, clearly perceivable improvement. And the acute decrease is on the first day achieved by 4 hours stimulation while patients are still kept off medication, is shown by these green bars. And you see that all patients but one had an acute, clinically significant improvement. And this patient also even did not get worse. And over the 3 months, what we see that all patients had a clinically significant improvement. The important thing is now that this also leads to, or what we observed in patients is that basically all patients reduced their medication, some really substantially by 90%, for example. And this is important because medication, there's a honeymoon. So if the degeneration of the dopamine producing cells in the midbrain reaches a level of about 50 to 60%, patients' motor symptoms show up. Then they have about, on average, 5 years with medication to cope with their symptoms. And then the efficacy of the medical pharmaceutical treatment vanishes, fades away, and side effects occur, and sometimes really, really disgusting side effects. And then DBS kicks in again for about 5 years. But the problem is, for both treatments, the actual symptoms, gait, balance, gait stability, freezing of gait, you'll see that in a minute, and voice and speech impairment, they're not adequately addressed by pharmaceutical and treatment and DBS so far. And for example, one of our patients, she was a ex-surgeon. She had horrible and typical side effects from agonists. For example, she had to stop being a surgeon simply because of the tremors, and she had to start shopping dessous online every night at between 1 and 2 a.m. for a couple of $1,000 a month, which is a typical side effect of agonists. So the compulsive behavior and impulse control is massively affected in about 20% of these patients. And this, in male, this very often leads to porn and other types of activities in women. There might also be a porn connotation, but it's very often compulsive shopping. And this destroys families and causes huge amount of suffering. And that patient, for example, got rid of was able to get rid of the medication after 3 days of glove treatment and didn't have any side effects ever since. So another very important and very surprising finding was the following. What you see here is the group analysis of all patients before off medication. Again, off medication and no medication interfering with EEG activity taken in general, not just PD medication. And this is the group analysis of the primary motor and primary sensory cortex. So it's the power analysis. And the only frequency band that showed a significant change was the high beta band between 21 and 30 hertz, a known frequency band. It's and it's intimately related to pathophysiology of Parkinson's disease. And what you can see, of course, after statistical testing, but already by visual inspection, is a huge, significant decrease from before treatment, so baseline, and after 3 months of VCR treatment, vibrotactile coordinated reset stimulation treatment. That's amazing because it's not trivial to find reliable biomarkers, cortical biomarkers. From the depth, it's simple to record abnormal rhythmic activity. But this was very encouraging for us because we didn't expect such a huge effect. Here you see 3 cases. I've treated already about 10 patients in Europe on a compassionate use base, which is way easier than in the US. And some of these patients are for four and a half years they came from really massively impaired states to being close to, according to family and friends, close to nearly normal states, and had no side effects, fortunately. And what we did was here is a case series in 3 patients, systematic case series. Again, all these data points, these clinical exams of the motor control, head-to-toe type of motor control exam, were off medication. Patients had a thorough withdrawal of their medications, and the x-axis is days of vibrotactile stimulation. So this is about 9 months, this is 5 months, and this is 6 months, 2 to 4 hours stimulation a day, 1 month pause, and this is again 3 months. This was the initial plan for our pilot study. This was the initial design. We wanted to go for another 6 months, but then, as I said, COVID hit us. So the important point is the following: when you monitor Parkinson patients, they deteriorate because it's a degenerative disorder, and they deteriorate, and the score increases depending on the population, Parkinson population type, age, and all this stuff, and stage of the disease, the disorder, by some like 3 to 5 points when assessed off medication over a year. So what you would expect is that the line goes up this way. Not too much, but steadily. There's a steady impairment. And the amazing thing here is patients really get better when completely off medication. And you see here, even with this maintenance dose, patients get off. And we were able to follow up 3 patients remotely, 6 months, 2 to 4 hours a day, 6 months, only a maintenance dose of 2 to 3 times 2 hours a week, so not much. And then they had after effects for between 9 and 1.5 years. So being on this massively reduced symptoms level with strongly reduced medication and being stable. So the after effects are really huge. in order to, but these are numbers, of course. I mean, that's a huge effect size. It means that after something like half a year, you induce a halvening of the symptoms, which is huge. That's the effect size of deep brain stimulation, but achieved long-lasting medication in the medication off. And in order to illustrate what these numbers mean, show you some videos. So this is a patient diagnosed in 2007, took a huge amount of Parkinson's medication. He was in an off time, about 50% of his time, meaning he had to lay down, lie in bed. And he used a 4-point cane, was supposed to use a wheelchair because he was falling more and more often. He's instructed to simply enter the room. That's a typical thing for Parkinson's patients when they enter or exit the room, or when they have to turn around, turn the direction, turn velocities, they have issues. And what you see here is the shuffling, the small steps per patient, and you see that there's no facial expression. The arms are not swinging. So this is typical Parkinsonian gait. He then came to us and told him to use as much medication as necessary. There's no instruction to reduce medication, just as much medication as necessary to feel optimal, to feel as well as possible. And this was easy in his case because he had a short-acting carbidopa-levodopa, and he dropped down from on the first day to 6, and that's where he remained since then. And this is now the situation. The first days of stimulation is now 4 years ago, more than 4 years. And this is the same patient after 4 hours of stimulation, 2 times 2 hours, 2 times in the morning, lunch break, sorry, 2 times in the afternoon. You see the beautiful gait, swing of the arms. That's the 6th day. After 3 days, he was dismissed. Oh, he went home. I mean, it was no awards. He went home and he was able to restart working. And then there was one thing that was quite striking, and we did not expect this at all. And that's something a couple of our patients already reported. The underlying Parkinson's is not just a motor disorder. It's a sensory motor disorder, also a disorder or an impairment that also comes with an impairment of sensory motor integration. But it's a massive, it's a multi-system degeneration, and it starts with the olfactory bulb. So there's an olfactory impairment. Our patients reported an improvement of smell and taste. In this case, he was able to smell and taste again. And we have, for example, one patient who came from detecting just 1 out of 40 orders correctly, but in the Pennsylvania smell test, to detecting all 40 correctly after 3 months of treatment. So that's why we are now very interested in degeneration and counteracting degeneration, degenerative process by means of this treatment. That's another patient, early stage patient that it came in, had the Parkinson's diagnosis at 27. That's off medication prior to vibratactile treatment. Patient did a lot workout to keep his condition as positive as possible. Was no longer able to do the workout simply because of the right-sided tremor in the upper and lower extremities, but also balance issues, massive balance. That's the so-called pull test. And you see he has issues with this. And this is the video he sent me after 6 weeks of vibrotactile stimulation. He's, of course, on medication, but was never able to do this workout before. There's another patient, and then I'll soon conclude. So it's first visit, first day, morning off, meds. And you see that this is called shuffling, fascination, these little steps. He has to exit the door. And how one typically provokes it is, for example, he kicks in again because he has to stop. How one typically provokes it is in a clinical setting is you ask patients to turn around And you see this pronounced shuffling. And the patient is not really able to get into a normal mode of walking. And that's his usual issue. And he was sometimes really sort of jogging instead of walking because he wasn't able to get into the smooth type of gait. And this occurred over and over, also when on medication. This is now after 3 months. This treatment is not turning on and off type of thing like standard deep brain stimulation. It takes some time. So this is what's observed after 3 months. The patient reported he hardly shuffles when on medication. So I was very happy. And this is off medication. That's the point where we do these off medication evaluations to see the actual situation without pharmaceutical intervention. And you see that patients already doing certainly better, but the right arm is not swinging. And when turning around, then we also shuffles a bit, but it's already way better than at the beginning of the treatment. And this is after 5 months. The two patients met, and they were both in our study. And this is now after 6 months and a 1 month pre-planned pause. And now what kind of theoretical studies, or where does math come into play here? On the one hand, we've developed all this based on predictions generated at the beginning, really simple phase oscillator models, very beginning without plasticity. Now with spike time independent plasticity, we take into account now structural, and additionally to that, structural and static plasticity mechanisms, because in order to explain particular phenomena, we can otherwise not explain. And we develop different types of stimulation patterns for different types of spike time independent plasticity curves in order to achieve very robust, long-lasting effects. And of course, we're coming up with a very detailed models and apply these techniques in order just to optimize stimulation patterns in terms of or with respect to propagation through a network. Because the important point is we stimulate only the fingertips, but the patients do have whole body effects. And this is something we want to further optimize. And outlook will also be that we do the same detailed modeling for the vibrotactile stimulation. All this was done for deep brain stimulation. And of course, impact on neurodegeneration. And just briefly, and that's the last slide, it started with the desynchronization-induced reduction of synaptic weights. And this was based on the observation, the computational observation that we can move a network from a strongly synchronized, strongly synaptically connected state to a desynchronized and weakly connected synaptic state. And the next thing was decoupling stimulation. Decoupling stimulation means we reduce the synaptic weights without necessarily inducing an acute desynchronization. So the focus is really on the long-lasting effects. And for example, you could do this type of stimulation whenever there's hardly any acute symptom. You could switch to this more effective decoupling stimulation. And also new type of approaches, reshaping network topology. For instance, by means of periodic multi-channel stimulation, periodic sequences, adequately time-shifted, adapted to spike time independent plasticity rules and parameters, which induce changes of the network topology, really massive changes for for example, use star-like networks, base coming from very different, topologically very different networks. Might be, for example, relevant for chronic stroke. And outlook, again, is to take into account metabolic changes in order to cope with neurodegeneration and leverage the entire potential of this therapeutic approach. And finally, I want to thank my great lab members. This is a theoretical physicist, a couple of really fantastic CRCs, psychologists who do really first-rate clinical studies, clinical research, Tina Manjalis, an ENT fellow. I want to thank my neurology colleagues, a statistician, and Roy Doll, who is a great external supervising neurologist. And I'm grateful for the substantial funding. And I thank you for your attention.